Hello friends, welcome once again to the CEC EduSet live lecture. In previous lecture we talked about radio physics, that is radiological physics, and today also we have come up with the another branch of physics, that is the another branch of applied physics, in fact I should say, that is the accelerator physics. We will try to understand about this physics, and we will try to find relationship between the accelerator physics as well as the radiological physics. And for this we have with us in our studios again Professor Dr. that is Assistant Professor Dr. Azhar Majid Siddiqui. He is Assistant Professor in the Department of Physics, Jamia Millia Islamia. And first of all, I would like to welcome Dr. Azhar Majid Siddiqui to our studio of the EduSet lecture once again. And I would like to tell all the viewers who are watching us at this moment that Azhar Majid Siddiqui have given immense contribution to various publications, about nearly 40 publications I would say, and these publications are basically on the use of accelerators. As today we are going to study and learn about this very topic, I think all the students who are watching us right now would be benefited from this very lecture. So sir, what is your say on this very topic?
So this is an exciting branch of physics, which is for the we have not talked about it in the last lecture, but then some connection will be there about the use of accelerated physics in medical technology as well. So I would like to first describe about what is accelerated physics all about, and how many kinds of accelerators are there, what are their working principles, and then how are they utilized, and finally I will come to the applications, and in applications we will point out the uses in medical radiology as well. So let me start my talk with this particle accelerators. This is an exciting branch of physics, hitherto unexplored, I would say. The particle accelerators, they are basically used to study the nature of matter. It was way back in 1930s that scientists have started using accelerating particles, and by particles I mean initially it was thought to be only a proton or a neutron that can be excited up to higher energies, but later on, as we will see in the talk, any element on the periodic table can be accelerated. So these are massive machines which accelerate charged particles through an electric field, and this acceleration has to take place inside vacuum. So whatever is happening is actually inside vacuum. That means one has to reduce the pressure of the whole equipment up to quite a bit of the vacuum has to be reduced up to 0.001 mm of mercury, which is the standard, and in most of the cases it is much lesser. The unit that they normally talk about is atmospheric pressures. Atmospheric pressures, one can understand, it is about 1 torr is about equal to 760 millimeters of mercury, and this goes down to 10 raised to power minus 6 torr, at which these possibilities exist. So one can actually accelerate these protons or electrons. Initially we will concentrate on our discussion on protons and electrons initially. So you can accelerate it up to any energy, and then scientists started using these accelerated particles to collide them with some target atom, and what is the outcome of this collision that is taking place. So the result of these collisions, that is being analyzed by scientists everywhere. The actual attempt is to probe the subatomic world. As I said in my yesterday's talk, the atoms are about a micron, not a micron size, I am sorry. The nucleus of an atom is about a Fermi size. One Fermi is 10 raised to power minus 15, and 1 nanometer is 10 raised to power minus 9. And the wavelength within which the electron can exist is about 10 raised to power minus 10 meters. So these are the dimensions that one has to probe. So if you have to probe these dimensions, you have to energize your particle and go deep into the material. So, as per the definition, a particle accelerator is a machine which makes protons or electrons, or in the latest cases any element for that matter, any charged particle, and take them to very higher and higher energy levels. This enables the scientists to probe the subatomic world. The early construction of accelerators, as I said, was way back in 1930s, and that was actually motivated by the efforts from the nuclear physicists. Nuclear physicists tried to probe this, what is there inside the nucleus. Was it what was there inside the atom was known by then. What was there inside the nucleus has to be known. So these particles had to be energized so that they are able to probe inside the nucleus. Now, about 80 years later, what we have as of now is about we will come to know in the next slide, also in the forthcoming slides. There are about 17,000 accelerators throughout the world, and lot of work is going on in this area. Almost all the accelerators will have the following three most essential components. You have to have a source of the particles that has to be energized. So the proton source or an electron source, that is one of the most compulsory parts. Second thing, as I said, there has to be enough vacuum. That means your system has to be evacuated properly. So the pump that evacuates it, up to what level it evacuates, how much is the vacuum that you achieve. Now there are issues, and each one of them, like these elementary particles, the source of elementary particles and extracting those particles, that itself is a different field. Achieving the levels of vacuum of 10 raised to minus 6 and 10 raised to power minus 9 torr, that is another field in itself, on which a lot of research goes on separately. And then you have to have some means of speeding up the particles. Now in this means, now these are the most essential parts of any accelerator. Now this means the energizing the particles means you have to subject them to the particles through some electric field. Since this is a charged particle, a proton or a neutron or an electron, since these are charged particles, now you have to energize them, which means you have to subject them to some electric field. So with the help of electric field one can energize these particles, and with the help of magnetic field one can essentially deflect the particles. So you can control the trajectory and you can control the energy together of both these particles. Now what and all can be actually accelerated, what and all can be energized. You can energize proton, you can energize electron, you can energize positron. A positron is a particle which is supposed to be an antiparticle of an electron. So one can argue that a proton is also opposite to that of an electron. How is positron different from proton? So the answer is the positron has the charge that is opposite to that of electron, but the mass of positron is equal to the mass of the electron. So there is a difference between a positron and a proton. Similarly, one can have an antiproton. A proton is a plus 1.6 into 10 to the minus 19 coulomb. Similarly, your antiproton will have a minus 1.6 into 10 to the minus 19 coulomb. I'm sorry, the previous slide. 1 second. Yeah. So an antiproton is also equivalent to the mass of the proton, but its charge is opposite to the mass or to the charge of the electron. So these are two particles, the positron and antiproton, that exist inside the nucleus. We cannot see them directly. You don't have the means to see them. One can only carry out a kind of an experiment to detect these exist or not, because their half-life is also very small. So there is some nuclear interaction taking place inside the nucleus. As a result of that, either a positron or some antiproton that is emitted, but those are short-lived. So when you do not normally come to know about it unless you carry out these high energetic and accelerated accelerator physics. Similarly, one can energize alpha particles. We talked about these alpha particles, what are there. So, you can energize alpha particles also, and the latest scenario, as I just said, the latest scenario is that any element on the periodic table can be energized, and those elements which can be ionized. So, which means, as we discussed yesterday, the gamma rays, you cannot deflect them because they are neutral in nature. You cannot deflect them using electric field or the magnetic field. So, similarly, any element that has to be energized, that has to be accelerated, should be ionized in the first instance. Once it is ionized, you can actually energize it up to energies. We will talk about the dimensions of those energies also in a short while from now. The accelerators normally follow, the accelerated particles, they normally follow a trajectory. This trajectory can be straight, it can be spiral, it can be circular. As I said, you can control this trajectory with the help of electromagnetic fields. You can focus these fields, you can defocus them. The terminology that is normally used for these focusing and defocusing of beams is nearly the same as you use in optics. In optics also, you use condenser lenses, you use a convex lens to focus a beam, you use a concave lens to defocus a beam, and that way, one way or the other, a combination of both of them as an objective, as an eyepiece. You use a telescope to see far off places, far off objects. You see a small microscope to enlarge something which is of the order of a micron size, your molecules, etc. All those terminologies can directly be taken into your beam physics, because this also is an electromagnetic radiation. The optics is also an electromagnetic radiation. The only difference is that optics has a wavelength of about 400 to 700 nanometers. We talk about those wavelengths, that is 4000 angstroms to 7000 angstroms. Which is the human range, which is the range in which one can see the colors, one can differentiate between them. Beyond these wavelengths, less than 400 nanometers and higher than 700 nanometers, one becomes blind to these radiations. One is the ultraviolet rays, the second one is the infrared rays, and human eye is blind to both of them. So, the radiations that one talks about in beam physics, the wavelengths of these, you compare it with 400 angstroms or 4000 angstroms or 400 nanometers, compare it with the lambda, with the wavelength of beams, this is about 1 to 2 angstroms. So, one has to control the trajectory of these particles and energize them. So, in order to control the trajectory, you have to have the same concept, condenser lens, in which one can focus the beam, one can defocus the beam. Somewhere the beam is falling where we do not want it to fall, and somewhere the beam is going slightly distracting away, you have to control that. So, it is the magnetic field that is used at those points, so that we can deflect the beam towards a particular point. So, this way one can actually control the trajectory, and one can control the energy also of the accelerated particles. So, depending upon what kind of path this beam is taking, one can divide the kind of accelerators into the following three categories. One is the Van de Graaff accelerator, the second one is the Linac accelerator, the third one is a cyclotron. We will talk about one by one all of these things. Now, the experiments that are conducted with particle physics, they are actually not confined to only research in how to accelerate. I would say the use of accelerator physics has expanded manifold. You can carry out your experiments in particle physics in finding out inside the nucleus what is there. Inside the nucleus there you have neutrons and protons, and now scientists are able to probe what is there inside the neutron also, what is there inside the proton also, and they have been able to find out to a good amount of success the elementary building blocks of these neutrons and protons, which are known as quarks. And in between these, the combination of these quarks actually have in various combinations they manifest themselves as a proton, as a neutron and as various other particles that are existing inside the nucleus, that those do not normally show up in the normal world. So, particle physics is that branch of physics where one has to actually probe inside the nucleon. You say nucleon because those particles which are staying inside the nucleus, like protons and neutrons and many other such particles, there are so many, those are all called nucleons, and one has to probe their building block. So, one has to, which means one has to energize your probe, your beam, your accelerated particles, you have to energize it up to a high amount of energies. We will talk about these energies in just a moment. And then there is another class of physics which is the nuclear physics, in which one has to consider what kind of nuclear reactions are taking place and how much energy is released and how can we harness those energies for the proper use in the society. Earlier it had been used for bombs, etc., and even now many countries possess these nuclear bombs, but then can we harness, instead of using it for the harmful uses, can we utilize this energy in a proper form which can be beneficial to the society. The third area which is normally covered using the accelerator is the condensed matter physics. So, one can actually probe inside the crystal how the atoms are arranged. One can utilize X-rays also. We have seen X-rays yesterday in our discussion. So, X-ray diffraction also helps one to find out the crystal structure, but there are other studies which tell us much more details rather than X-rays, and those studies are actually can be made possible only with the advent of accelerator physics. So, the condensed matter physics and the materials science, that has been benefited a lot from the accelerator physics. The experiments that a particular accelerator facility, the experiments that have been carried out are very specific. What we do at Inter-University Accelerator Center at Delhi, what we do at CAT Indore, what kind of experiment has been carried out at other places wherever the accelerators are present, for example, Institute of Physics Bhubaneswar, and then Indira Gandhi Center for Atomic Research Kalpakkam, and then a couple of accelerators at one such accelerator at IIT Kanpur, and there are small places where we have these accelerators. Initially it all started with one such accelerator at Bhabha Atomic Research Center. Then we had one facility at Tata Institute of Fundamental Research, Mumbai, and then all those things have been shifted over, and there are many such accelerators within India also. We will try to cover this aspect at in a short while from now. Now, coming to a brief description of these accelerators separately, we have one Van de Graaff accelerator, which was one of the very first to be designed. This was designed way back in 1920s, the late 1920s. The one that was known, that was designed by Cockcroft and Walton, the two British scientists, they could accelerate protons up to 250,000 electron volts. 1 electron volt, let me tell you the dimensions also. 1 electron volt is about 1.6 into 10 raised to minus 19 joules. So, if you convert, one can have a direct conversion into how much will be in joules, but then what you can see here is that this is essentially a multiple of voltages in which this has to be done. So, 1 electron charge is 1.6 into 10 to the minus 19, and then that is to be multiplied by 250,000 times. That means you have to develop that much voltage, that much electrostatic field has to be generated. Now, with this field, the moving of the belt, what you see here is this movement of the belt is actually helping in driving the charged particle from one pulley to the other. In the place where this drive pulley is written, behind that is an accelerator tube. One can imagine, okay, this is a two-dimensional image. So, there is an accelerator tube there, and with inside, which is evacuated, of course, up to a high level of vacuum, and the proton or electron is actually moving inside, or any other charged particle, they are all moving inside that acceleration tube. Now, because of the charge induction, you can see there is an inductor there. because of this charge induction helps in moving this particle from one pulley to the other, and because of this charge induction only, there is a negative charge that is on the lower side of the belt. So this belt, it takes a complete rotation, and the beam is moved from one place to the other. A similar system was later on built in the early 30s by an American physicist by the name Van de Graaff, and the accelerator was therefore called the Van de Graaff accelerator, and one can go up to 15 million electron volts using a Van de Graaff accelerator. We have one such facility at Inter-University Accelerator Center in Delhi. There one can actually energize the particles not just up to 15 MeV. There are 3 separate accelerators. The one on which material scientists work, one in which I also specialize, there you can energize all particles on the periodic table, all elements on the periodic table up to 200 MeV, 200 million electron volts. So this much acceleration is possible now. This is about your Van de Graaff accelerator. Then you have another accelerator by the name LINAC. LINAC is essentially a linear accelerator. This was designed again in the late 1920s, so one can see a lot of work scientists have started a lot of efforts in this area, because this actually helps them in understanding what kind of matter is there inside a nucleus. Now we talk about the presence of Higgs boson and people trying to catch it, and how much energy will be needed to actually see the Higgs boson. Can we really see? Those possibilities have become, have come to a reality only now in late 2010, I can say. But then the efforts had started way back some 18 or 90 years back. So here what you essentially do in linear accelerator is that you use a hollow tube, a series of these tubes, not just one tube. There are a series of tubes. Each tube is energized up to a certain level. So the particle that is actually entering from the left hand side, the injected particles, and this particle is actually generated from a Van de Graaff generator. So that means it is actually initially it is having some energy, and then as it passes from one tube to the other, it gains some energy. So at each successive emission and re-admitting into the tube, the energy of the particle is multiplied. So this is one such figure where the Stanford University, the LINAC is about 3.2 kilometers long and it is capable of accelerating electrons. They normally use it for energizing electrons up to 50 giga electron volts, and 1 giga, one can understand, is about 10 raised to the power plus 9. So this is 50 billion electron volts that one can achieve using linear accelerators. Now the third one, which is all the more interesting to see, and I will spend a little amount of time on this only. This is a cyclotron. Cyclotron is somewhat like a LINAC only. It works on those principles, but then that LINAC has been wrapped around in circular shapes. So many tubes have actually been shaped into a kind of a tube. I will show this on the transparency. That would be a better thing to show. You see so many rings through which an electron or a proton is going through. Now each ring, which means this source of proton is coming, is emitting protons, and this proton is following a spiral kind of a path. At each intersection, each gap, it comes out one D. These are two Ds because of their shape. They are called Ds. When it comes out of each D, it gains some energy and enters into another D. So the radius of curvature, I don't have that equation written here. I would have liked to show it, but anyway, the equation is something like mv squared by r, m into v squared upon r. M is the mass of the proton, v is the velocity of the proton, r is the radius through which it has to go through. that is made equal to mv squared upon r, that is made equal to, one second, q into v into b. That q is the charge of the proton, v is again the velocity of the proton, and b is the magnetic field through which it has to go through. So once having fixed this radius, one can keep on increasing the magnetic field. Charge is fixed, mass is fixed, what you can vary is the radius, and that radius can be varied by varying the magnetic field. The amount of magnetic field through which it has to go through, that is varied, and the proton gains energy at each and every such step. So that way it eventually comes out, it gains so much energy that it eventually comes out of the spiral, but the energy that it spends and how much it will be the length of this d, that is very interesting to consider. You can go up to that depends on how much energy up to which you want to accelerate your proton or an electron. So let me show you an example and let us see an outcome of that example. That is very interesting. This is a synchrotron which is basically placed at CERN Geneva. This is placed in Switzerland, Geneva. Now the accelerator of this CERN is about 27 kilometers in circumference. The radius is something like 7 to 9 kilometers or some such radius. It covers the border of France and Switzerland together, and when they expanded it, the countries, I don't remember how many countries it passes through. What I know for sure is that the whole tube passes through 5 countries now. So the proton starts at a place in CERN in Geneva and keeps on rotating till it enters into France and then other countries and re-enters into Switzerland and goes back into France and keeps on doing the circular motions, and then at one such place you can simply extract it. So it is energized up to 450 giga electron volts. That is what you see on your computers, on your TV screen. So 400 at these energies, scientists have been able to break inside the nucleon, not just nucleus, the particle that is residual of the nucleus, the neutron and the proton, and what goes on in between them, what kind of reactions that actually go on in between them. Those have been recorded with the help of such accelerators only, and the outcome, an offshoot, I can say. Very few people normally know. We in accelerator physics branch, almost everywhere in the world, whosoever is working in accelerator physics knows this fact, that the internet, the advent of internet is actually a brainchild of 2 accelerator physicists. I have mentioned this particularly to incite some interest among all the students, because normally people don't know how this possibility became a reality, that you are transferring some information on your computer, it goes through, within a millisecond it reaches the other end of the world. How has that become possible? It has started at CERN Geneva, where 2 scientists were supposed to take down data sitting at a place in Geneva, and they have to transfer that data. I mean, you see the ring here, 5th or 6th ring. After that 5th or 6th ring, they had to collect some data and then copy it into a floppy. In earlier times, in 1980s, early 1980s, there were only floppies existing. They had to copy that data into floppies and then physically take them into their hand or post them to another country where the analysis has to be done. And this was going on for quite some time. It went on for quite some time, but then they themselves thought that why not we transfer this data, we convert this data into a digitized signal and then send them the way a phone call is being sent, send them through this phone line. And the rest is history. We all know in 1982 internet has taken birth, and what it has done to the whole world we all understand, the email and then so many other applications of internet. So one of the offshoots of accelerator physics, which is normally not known in other areas of science, one of the offshoots of accelerator physics itself is the birth of internet. So the cyclotron, as I was telling just some time back, the cyclotron is it was first designed in 1939 by an American physicist by the name Ernest Lawrence, who won a Nobel Prize in 1939 for this design. This was a big breakthrough. He developed the cyclotron, and the magnetic field produced by a powerful electromagnet that keeps the particles moving, as I just described, q mv squared by r equals to q into v into b. This equation guides those particles into which trajectory, which radius it has to go, given this magnetic field, which is the radius suitable, so that this equation is satisfied. That way they are able to control the trajectory up to high level of accuracy, very high level of accuracy. Now each time the charged particle passes through the gap between the Ds, it is accelerated because there is an electric field present within that gap of 2 Ds. So at each such gap, the particle gains energy, enters into a new ring of a different radius, and is energized again at the exit of that. So that way they are able to gain energy up to 450 giga electron volts. This is one such figure of CERN. The figure may not be very clear, and many of my these things are from directly taken from the internet. So I don't have right now the clear photos of these, but then one can see the ring very clearly there. That ring is, this is a bird's eye view of this whole accelerator, which is underground. The ring does not exist over the ground. You cannot see it from outside. This is just a layout that has been given, and a schematic is there on the right hand side corner, where one can see 2 rings. One is the ring where the protons are accelerated, P is written there with an arrow. From the LINAC, this proton enters this beam. LINAC is written there, a proton is entering. You can take this proton directly and use it from the LINAC at a smaller energy. One can also send this proton to the booster, from where it becomes a source of the proton, and that source of the proton goes inside the cyclotron. So this way now it is made to go through n number of such circles. I mean, it is rotated n number of times inside those circles, so that it is energized up to the required energy levels. And what we see here is a proton that is up to any energy, giga electron volts they talk about. As I said in my initial lecture, it is estimated that there are about 17,000 accelerators in operation. They have been used in the world everywhere, in industry, in hospitals, at research institutions. We have n such institutions in the world. In India, we give here some of the applications of particle accelerators. The first one to utilize this in material science is the semiconductor industry. This semiconductor industry relies heavily on the ion implantation. I will spend just a couple of minutes on this. Normally what we know about semiconductors is that silicon is having 4 electrons in its outermost orbit. With those 4 electrons, it is not able to do whatever it is supposed to do, the conduction mechanism that it should act as a good conductor or as a semiconductor properly. So it has to be doped properly. Once doped, it becomes an n-type semiconductor or a p-type, depending upon what kind of impurity you are mixing in. Now the mixing of this impurity through chemical routes is possible, easy, very cheap, but then you cannot control up to how much level of depth you can achieve in mixing this impurity. This impurity can stay right on the surface, it can go inside the material, but up to what level, how much you can control the range of this impurity. What you actually can do with the help of accelerator is that yesterday we talked about the range of alpha particles, the range of beta particles, the range of gamma and X-ray. Now with accelerator, I can control the trajectory of alpha particle, the trajectory of proton, the range up to which it can go, I can control all these things up to whatever level I can manage. So inside the material, well, let us say I have an alpha particle which is energized up to 4 MeV, 4 million electron volts. The alpha particle inside the material can go up to 1 micron. Now, if I have to mix an impurity like phosphorus in silicon, the energy up to which I can energize it is something like 1 million electron volt, and this 1 million electron volt goes up to some 5 microns inside inside silicon. You have a separate study altogether a separate study about the range and the energy. This particle, this energy, how much deep it can go into which kind of sample. This complete table is there. One can simply have a look at the table, energize your particle up to that level, and then achieve the level of impurity that you want to mix. You want to mix 10 raised to power 13 atoms in a small area of 1 centimeter square, 10 raised to power 16 atoms in 1 centimeter square. You can have a total control over this doping, total control over the diffusion this doping can, this impurity can diffuse into. So that way the semiconductor industry has relied heavily on the process is called ion implantation. There is another process associated with this same thing which is called the ion irradiation, where we are not bothered about impurity staying at 1 micron. The impurity can go deep down up to let us say 20 micron or so, but I am interested in seeing only a few top layers, which is my area of specialization, which happens to be my area of specialization also. Then this is called ion irradiation because the ion has gone inside the material and it has gone up to quite deep down, and I am seeing what has actually happened to the surface. So semiconductor industry, coming back to my this thing, semiconductor industry relies heavily on accelerator technology so that you can have a controlled level of impurity mixing inside semiconductors. That is one such area. The second area is the clean water, clean air and clean water. The studies show that blasts of electrons, electron acceleration in this case, from a particle accelerator are a very effective way to clean up dirty water, sewage sludge and polluted gases, etc., etc. Nuclear physics, this actually is an particle accelerator physics itself is a branch, I will say, that has come out of nuclear work on nuclear physics only. So obviously we have enormous applications in nuclear energy. One can have enormous potential to how to treat the nuclear waste, what these energetic particles can do, how can we harness that nuclear waste, can we are we able to use it for as an alternative fuel. A lot of work is going on there. So the third area on which accelerator physics finds its application is nuclear energy. Then we have a lot of work going on in DNA. That would be really new to most of the people. Synchrotron light sources also allowed scientists to define, to see the DNA, because if I can probe a nucleus, if I can probe inside the nucleus what is there inside the neutron, what is there inside the electron, the proton, not electron of course, what is there inside the proton, then I can as well see what kind of a DNA, what kind of a molecule it is, the DNA mapping, etc., and lot of research goes on in that also. Then in pharmaceutical industry, the pharmaceutical industry also is one such area where one can work on. Then industry is also using particle accelerators to produce very sturdy heat shrinkable films. There is a lot of work. Another area that is finding immense application is the biomedical. In the biomedical, I will say, the people are using, if I remember correctly, it is tantalum or titanium. Tantalum, I believe. I am not that specialist anyway. Tantalum has been implanted with gold, and that has been found to be as much strength as a human body bone. So can we replace that? If there is a fracture which has gone beyond repair, so can I just remove that bone and instead implant an implanted tantalum into it, and then how long can that tantalum stay inside my body, how will it react, how much wear will take place. So this is another area in which lot of work is going on. And then films that are being made heat shrinkable, can they be used in food industry, etc. Of course, medical diagnostics, radioisotopes. If I can create this, if I can energize and create some nuclear activity artificially, and so that I can treat a particular ailment using that particular, for example, alpha particle that does not go quite deep inside my body, but it does not have harmful effects also. So if I can have an alpha particle which I can energize it and then send inside the body, which is slightly having some difficulty. So this is another area of medical diagnostics. And finally, of course, yesterday we talked about cancer therapy. In cancer therapy also, one comes to know about when it comes to treating certain kinds of cancer and etc. Now finally, I will give a small...
we will be proceeding further. Before that, I think we should take a call, because caller is there with us,
okay,
and we'll proceed further with this. We have a call from Kolkata, I think. Hello.
Hello.
Ji, please ask your question.
Hello. Sir, I'm Sahil.
Yes, please speak loudly and ask your question.
Assalamu alaikum.
Ji, assalamu alaikum.
Yes, sir. Sir, I want to know positron.
Sorry, your question is not clear.
Telephone line जो है disconnect हो
Okay,
चुकी है.
so let me just show you in a glimpse. I will show you a scenario of accelerator physics research in India. The slide shows, one can go through this website where this is documented of all the research activities that are going on in India. The website, it's written here, www.ias.ac.in. Pramana is one such journal where this is published in November 2002. This particular article, it has enlisted what and all research activities are actually going on in India, including the one at the Inter-University Accelerator Center, which is in Delhi itself. Earlier it was known as Nuclear Science Center, now it has been named as Inter-University Accelerator Center. This is a major research facility which is being provided to all university users. Whosoever wants to work in the field of accelerator physics is welcome to submit their proposals here. So they also encourage this work for all university users basically.
Definitely, sir. I think most of the students who are watching us would be reaching this site and trying to find out more things. Now my question is, as we have discussed about various things and you told us about various things. Now my question is, what are the antiprotons? With the protons, we are clear that they are the positively charged.
And proton is a positively charged particle which is a building block of the nucleus. Proton, you have a proton, you have a neutron. Protons are positively charged, which are opposite to the charge of the electron, that is there. But then within the nucleus, protons and neutrons are also undergoing so many reactions which are very short ranged. So this proton is having the charge opposite to the charge of the electron.
Okay, electron.
But antiproton has a charge which is opposite to the charge of the proton, but it is not electron.
We'll be talking on this particular topic, this particular issue. Before that, we have a caller with us from Uttarakhand. Hello.
Yeah,
Hello.
Good afternoon, sir.
Good afternoon.
Please ask a question.
Sir, I want to what difference between proton, neutron and electron, and what is the latest theory of this field?
You want to know about the electron, protons, neutrons as well as?
Neutron, and what is the latest invention of this field?
Latest invention.
Latest invention.
Okay. Protons and neutrons, we were just discussing about this only. Protons and neutrons are those residual particles inside the nucleus. Inside the nucleus you have proton and neutron neutron is a neutrally charged particle. Proton is positively charged. So the charge of the nucleus is also always positively charged because of the presence of proton only, but the mass of the nucleus is because of the mass of proton plus mass of the neutron as well. But then there are other particles also which are present inside the nucleus which are very short lived. One such thing which I was just discussing is antiproton, which has the charge which is equal to the charge of the electron, minus 1.6 into 10 to the minus 19. But the mass of this antiproton is equal to the mass of the proton. So it is something which is similar in mass to protons but similar in charge to electron. So that is your antiproton.
Yes.
And the research that is going on
Yes, sir.
in this area is that they are trying to probe inside the nucleon. A nucleon is something which stays inside there. So proton and neutron and antiproton and mesons, and there are many such particles. All of them have their own fundamental structure, their own fundamental block, building block. Now that building block has to be probed. So there are 6 kinds of quarks that are existing. A combination of these quarks gives you, these quarks manifest themselves in such a way that what you see outside is a proton. So inside the proton there is some structure, but inside the that structure is a structure or not, that is not known so far. Maybe we can achieve that sometime later. But then as of now, where we stand is that a proton is composed of 3 quarks. A neutron is also composed of 3 different kinds of quarks. Now there is an exchange of more short-lived particles in between this proton and neutron, so the nucleus remains stable that way. So this is the work that is going on, and the latest what you have just heard is that this Higgs boson, a trace of Higgs boson, you have not seen the Higgs boson actually, a trace of it could be actually found out. People are trying to, conclude whether it was really a Higgs boson or not.
Exactly,
Yeah.
Experiments are going on,
Experiments
and
are
we
still
hope
going on, yeah.
we could
Many
get success in near future. My next question is, sir, what is the trajectory? If we talk about it in simple terms, if we are talking about the movement of the particles
Movement
from
of the
one
particle,
end to
yeah,
the
from
another
one
end,
end
but
to
what
the
actually
other.
trajectory is?
I'll show you the transparency here, which is quite interesting to see. Now, what you see is the moving belt, and inside the moving belt there is something hollow space in between them. That hollow space is actually not hollow, it's a small, there is a small acceleration tube there. Inside that acceleration tube, your proton or your electron or any other charged particle is being accelerated. Now once that is accelerated, you cannot guarantee that it will go in straight line only. So once it has some energy, it will follow some kind of a wavy kind of a motion. So that has to be controlled. So that is what we mean by controlling its trajectory. What we mean is that we subject it to some kind of a magnetic field, so that I can control where I can focus it and where it has to go away from. So that can be done with the help of using a magnetic field.
With the help of the
With the help
magnetic
of the magnetic field. The equation is QVB equals to mv squared upon R.
Before I ask my question further, I
There's some
think we
question,
should take
yeah.
a caller, a call from Punjab. Hello.
हेलो
Yes.
जी मैं आपसे पूछना चाहती हूँ
जी।
कि हम जो एनर्जी प्रोटॉन्स को देते हैं, क्या वो सारी की सारी यूज कर ली जाती है?
Almost at all the places we use all the energies. जो material science में use होती है, वो तो 200 MeV की 200 MeV सारी की सारी उसमें टारगेट में इम्पार्ट हो जाती है. और जैसे आयन इम्प्लांटेशन में आपने एनर्जी यूज़ की, वो सारी एनर्जी, दिस डिपेंड्स ऑन how much you are able to control the energy of your probe. Your probe means your energetic particle. अल्फा पार्टिकल 4 MeV की है, तो 4 MeV सारी की सारी आपने उसको इम्पार्ट कर दी, वो 4 MeV से ट्रैवल कर रहा है. Now if it is traveling with 4 MeV, it goes and stops. It does not stop, it can go inside, but that much amount of energy it has actually imparted on the target. Similarly, your protons, when they are accelerated and made to fall on any matter, they are imparting all that energy to that matter, and then you are utilizing what are the after effects of that. So almost all the energy is utilized. Sometimes your question is good, very good. I am really happy that somebody has raised this, कि अगर हमने पार्टिकल को एनर्जाइज किया तो क्या उसके साथ कोई और इफेक्ट भी होता है, तो वो थर्मल इफेक्ट सबसे ज़्यादा नज़र आता है. लोकली टारगेट कैन गेट हीटेड अप, जहाँ पे बीम गिर रही है वहाँ पे टारगेट के एनर्जी बढ़ जाती है तो टेम्परेचर बढ़ जाता है और बहुत तेजी से बढ़ता है और बहुत तेजी से घटता है. But then one can utilize that changes in the temperature also.
I hope she might have got her answer. Another caller from Uttarakhand. Please ask your question.
Sir, what is quantization of charge?
What is?
Quantization of charge.
Concise.
Quantization.
Yes, he is
Are you
asking
talking about
about.
quantization of charges?
Of charge.
Yes, he is asking about the quantization of the
Quantization
charges.
of charge. Quantum means a packet. So charge quantization means then he might be asking about something about the quantization of charges in the sense of inside the proton, inside the neutron, inside the proton and a neutron you have a quark. Now that quark is actually having a charge which is 1/3 the charge of the electron. So the second quark will also have the 1/3 of the charge of the electron. So three of them together give you the charge of one proton. So this is that change from 1/3 to 1/3. This change is actually the quantization of charges. But then one talks about those quantization of charges only in the sense of high energy physics, in the sense of only I mean looking inside the structure of the proton or a neutron.
Hope our dear friend would have got his answer correctly. Now my question is, the girl from Punjab, I think from Uttarakhand, she asked the question of about the energy. जी सबसे पहले कॉल ले लेते हैं. अगले कॉलर जम्मू कश्मीर से हमारे साथ जुड़ चुके हैं. हेलो, यस प्लीज आस्क योर क्वेश्चन.
आदाब मैडम.
यस, अपना क्वेश्चन पूछिए प्लीज.
आदाब मैडम.
जी
मैडम मैं ये क्वेश्चन पूछना चाहता हूँ.
जी.
What is difference between beta particle and electron?
Yeah, beta particle and electron. Beta particle is also an electron, but then that electron which has actually taken birth inside the nucleus as a result of some nuclear interaction. There are many interactions taking place. What we see as stable nucleus is inside it is not so stable. So many things are actually going on for a small short interval of time, 10 raised to minus 13 seconds, 10 raised to minus 15 seconds. Within that interval, so many reactions take place, and through some reaction an electron is generated inside the nucleus. But that electron which is generated inside the nucleus cannot stay there inside the nucleus because its wavelength, the wavelength of the electron, because electron is also a wave as also a particle, so its wavelength is much larger than the size of the nucleus, so it has to come out. When it comes out, you call it a beta particle, otherwise it's an electron only. So that is the only difference between them. An electron that stays in atomic orbitals, a beta particle is an electron that has taken birth inside the nucleus and has spontaneously come out.
Now moving towards my question.
Yeah.
Another call from Uttarakhand. Hello.
May I proceed now?
जी प्लीज अपना क्वेश्चन पूछिए.
Yes, sir. Actually, in particle accelerator, one proton is accelerated up to 100 or above giga electron volt. There is a due to relativistic effect due to mass increase and density contraction.
Exactly.
Its density reaches up to the range of weak interaction range. So the constant quark of proton should disintegrate proton into neutron, neutrino and positron. So before reaching up to Higgs boson production, proton will burn up.
So what's the question?
I think our friend is trying to give us some input regarding this.
No, but what he has pointed out is correct. I will show in the transparency here. The energizing a proton up to these energies, I mean when you make them pass through such heavy energies, that means the protons will actually reach, what he said is really correct, that the mass changes because the relativistic effects come into picture. Once you achieve these energies, the particles, they are able to reach those velocities where their velocities become comparable to the speed of light. Once that happens, there are noticeable changes taking place in the mass of the particle itself. Now that has to be actually accounted for, which is what is a synchrotron at
So
CERN.
we'll be going towards synchrotron after taking this call. This is a call from Uttarakhand. Hello.
नमस्कार सर।
जी नमस्कार, स्वागत है आपका.
नमस्कार.
Please ask a question.
नमस्कार मैडम, मैं जानना चाहता हूँ हिग्स बोसोन थ्योरी क्या चीज है, इसके बारे में हमें जो है बहुत ही उत्सुकता है, इसे जानना चाहते हैं।
क्या चीज जानना चाहते हैं?
हिग्स बोसोन थ्योरी क्या चीज है? तो
हिग्स बोसॉन एक्चुअली, ओके चलिए, मैं मतलब जितना मैं जानता हूँ ये मैं बता सकता हूँ, बिकॉज आई एम नॉट फ्रॉम दैट फील्ड ऑफ हिग्स बोसॉन. पार्टिकल फिजिसिस्ट ये जो काम करते हैं, तो ये पार्टिकल फिजिसिस्ट ने इन्हीं एक्सेलरेटर की मदद से ये चीज़ पाई है कि जो मास ऑफ एनी फंडामेंटल पार्टिकल, मास जो आया है ये कहाँ से आया है, फ्रॉम वेयर इट हैज़ कम, हु इज रिस्पॉन्सिबल फॉर दिस मास. तो थियोरी तो मैं अभी आपको बता नहीं सकता, बिकॉज आई एम नॉट इन दैट फील्ड, लेकिन दिस इज वन ऑफ द कॉन्ट्रीब्यूशंस ऑफ सलाम, यू मस्ट हैव हर्ड, the Abdul Salam Center for International Center for Theoretical Physics. सलाम वाइनबर्ग, इन दोनों ने मिलकर एक ऐसा काम किया था जिसमें इन्होंने इलेक्ट्रोमैग्नेटिज्म को और न्यूक्लियर इंटरैक्शंस, न्यूक्लियर एनर्जी, न्यूक्लियर फोर्सेस को, दोज न्यूक्लियर फोर्सेस विच आर वेरी शॉर्ट रेंज इन नेचर, इन दोनों को कंबाइंड फॉर्म में कैसे लिखा जाए वो लिख के बताया था. तो एज एन आउटकम ऑफ दैट थियरी, वाइनबर्ग सलाम थियरी, एज एन आउटकम ऑफ दैट there are many such theories in which they wanted to unite all the forces. We have four kinds of forces existing. One force is your gravitational force. एक तो gravitational है जो कि हमको ज़मीन की धरती की तरफ खींचता है, अगर हम चांद की तरफ जाएं तो वो चांद की तरफ खींचता है. तो one is that gravitational force. The other one is the electromagnetic force. The third one is your nuclear short nuclear forces, which are short range nuclear forces. Then you have these strong nuclear forces. तो weak nuclear forces और strong nuclear forces और electromagnetic forces, तीनों को इन्होंने एक जा करके एक इक्वेशन लिखा था. and efforts are going on to unite this gravitational force also. इन्हीं efforts में ये बात पता चली कि it is this Higgs boson which is responsible for the mass of the...
I hope the caller might have got his answer. We have another caller waiting for us. That is the another force waiting for us to take the call. Hello.
Yeah.
Hello.
Sir, I am asking for meson particle found in nucleus.
You want to ask that Higgs boson particles found in nucleus?
No, meson particles found.
Mesons. Okay. Mesons, मैंने अभी जस्ट बताया था कि within the nucleus, again something which is slightly deviating from my own field, within the nucleus you have protons and neutrons which are bound together through some forces or the other. Now these forces which are actually binding these nucleons together, there is some exchange of particles taking place within a proton, from a proton and a neutron. These two, proton is positively charged particle, a neutron is neutral in nature. So what makes them bound together? It is the exchange of these mesons. A meson comes out of the proton, goes inside the nucleus, but then another meson which is anti to this meson, that comes out and joins this, and this proton becomes
our caller
this
might
thing.
have got the answer, because we have very few seconds left.
Okay.
With this note, I would take your leave. That is my all the viewers' leave, and hope we would be meeting again
so much.
and discussing on new topic. Thank you so very much,
Thank
Dr.
you so much.
Majid, for being with us in this EduSec lecture of ours. Thank you.
Thank you.